this presentation, we're going to discuss structured text. That's the third of the 4 languages that you can program with the support of the Logix engine. Structured text is basically just a text-based language. As a matter of fact, I started with Fortran and then eventually went to BASIC, and that's many years ago. And when I look at structured text, I don't see a whole lot of difference personally. So I know they have all these different structured text languages, C, C++, etc. Structured text is really pretty easy to write. I typically don't use it except for math. If I have a mathematical calculation that I have to do in my program, then I usually create a program file with structured text, and that's all it does is just calculate that particular expression. And I have no actual logic in there, just mathematical calculations. So first we're going to take a look at structured text as a language, and then when we're done with this presentation, then we're going to do another one where we're going to do some logic with structured text. So let's start with this one, just structured text language. Presentation specifically on languages, programming languages that you can use in the Logix engine. In addition to this one, we did ladder logic diagrams, which really was very brief because ladder logic diagrams have been covered extensively in the Complete PLC Learn series, with dozens of videos, and in RS5000 Volume 1 with all of those videos. So the ladder logic diagram component of the languages of the Logix engine was very rudimentary. It basically emphasized the differences between what RSLogix 500 and RSLogix 5000 supports. The other 3 languages, function block diagrams, sequential function charts, and now this one, structured text, goes into considerable more detail than we went into with ladder logic diagrams. If you are just joining the lectures with this presentation, you picked a bad spot. We assume that you have watched all the previous videos, including the Complete PLC Learn series and RS5000 Volume 1 videos, that you've done all the exercises, all the labs. However, this lecture is standalone in a sense if you are already an experienced programmer. Now, structured text, a textual programming language that uses statements to define what to execute. It's not case sensitive. It uses tabs and carriage returns, separate lines, to make your structured text easier to read. And they have no effect on the execution of the structured text. Structured text is probably the most popular for computer science majors who are moving over into the industrial control field, primarily because it's what they're accustomed to. However, out on the shop floor, and let everyone here who is listening pay close attention to this. The name of the game in manufacturing is quality out the door. Production out the door without defects in it. To do that, you have to have a high uptime, which means if something breaks, you have to find it in a hurry using your laptop with RSLogix 5000. Structured text is the most difficult language to troubleshoot with. Now, someone who's done nothing but text-based languages may want to argue that. I have always issued the challenge to anyone out there who uses text-based language to program a machine of medium convolution. I will challenge you both to write the code and to troubleshoot it. You use text-based language, I'll use ladder logic diagrams. Now, typically, I use at least 3 of these languages. I don't do a lot with sequential function charts, although they are very elegant and they have a beauty all their own. Typically, if I'm going to use structured text, I use it for math. The Logix engine, if you have one of the, we'll call it the more capable processors, you can have up to 32 tasks. Each task can have 100 programs, Each program can have an almost unlimited number of routines, add-on instructions, subroutines, etc. Each routine in a program can use one and only one language. I quite often will create a routine with structured text that has a fairly complex mathematical expression in it, but it references a tag from the tag database, and then it influences another tag in the tag database. That output tag, if you want to call it that, from the math expression is used in the other languages. I'm not de-emphasizing structured text. Structured text is the perfect language for certain portions of your program, but I encourage you to consider at least ladder logic diagram, function block diagrams, and structured text when you're writing your code. Structured text is not case sensitive. To make your code easier to navigate, use tabs and carriage returns. And we start with something called an assignment statement. Use an assignment statement to assign values to tags, not to create tags. Text-based languages, quite often the very first thing you do is declare your variables. In structured text, it uses values from the tag database and influences values in the tag database, but it's the same tag database that all four languages use. And the variables are declared in the tag database. Now you can actually create a tag while you're writing the languages and then declare it or define it. However, you don't begin your structured text with a half a dozen or a dozen lines of declaring your variables. But if you want to assign a value to a tag, tag : equals expression or a value. The : equal is the assignment operator. Terminate the assignment with a semicolon. A structured text program will be run from beginning to end many times each second. A traditional program should not reach the end until it is completely finished. If you're accustomed to writing text-based programs that actually sit and wait for certain conditions and don't keep executing all of the code, this is going to be a little bit different. You can't pause the processor for seconds, minutes, even hours waiting for some condition. You continually, in other words, there's a continuous task and it is continually executing something. If this were to happen during a control application, the controller would stop responding. You'd have a watchdog timeout. The process might become dangerous and the controller watchdog timer would force a fault. The language is composed of written statements separated by semicolons. So you could say that the rungs of logic are separated by semicolons. The statements use predefined statements and program subroutines to change variables. The variables can be explicitly defined values, internally stored variables, or inputs and outputs. Spaces should be used to separate statements and variables, although they are not necessary and they do not affect the execution. Structured text is not case sensitive, but it can be useful to make variables lowercase and make the statements uppercase. Indenting and comments should also be used to increase readability and the documents of the program. Comments that are added to the structured text explain the text. This is not necessary with the other languages because it is already apparent. Typically, my tag names use what I call case delimiters, meaning to make it readable I leave out the spaces because you can't use a space in a tag name, and an underscore kind of clutters it. If I had a tag value in, I would capitalize the V on value and the I on in. It's kind of a textual delimiter. It's not really a program delimiter. Back to expressions. An expression is a component of an assignment or a construct statement. An expression evaluates to a number if it's a numerical expression, or if it's a Boolean expression, then it evaluates to a true or false state. An expression contains tags, and a tag points to an area in memory where data is stored, such as value 1, and it's going to be in one of the atomic data types: Boolean, single integer, integer, double integer, real, or string, and I believe in some cases long integer. An expression besides tags contain immediates, which would be a constant value, Operators, a mnemonic or symbol that specifies an operation within the expression, like plus, minus, greater than, less than, equal to, etc. Functions, the execution of a function produces one value. Use parentheses to contain the operand of a function. In this case, for arithmetic functions, you could have absolute value, ABS, arc cosine, arcsine, arctangent, cosine, radians to degrees, natural log, log base 10, degrees to radians, sine, square root, tangent, and truncate. Those are the arithmetic functions. If you have a value in tag 1 of 90 and this function is sine, what you're going to get back is the sine of 90 degrees. Functions can only be used in expressions. Instructions cannot be used inside an expression. An instruction is a standalone statement that executes against a variable. An instruction uses parentheses to contain its operands. Instruction dependent, there can be one, multiple, or even zero operands. Upon execution, an instruction can produce one or more values that are part of a data structure. For instance, instruction, and you have 3 operands in the instruction. A construct, a conditional statement used to trigger structured text code. If, then, case, for, do, while, do, and repeat until, and exit. These are constructs. We use this terminology in ladder logic sometimes when we're describing the logic of the rung. Constructs are terminated with a semicolon. Normal text used to clarify or explain the functions of a section of structured text. Comments have no effect on execution, and they are not executed. They're simply there as a visual aid to anyone who's looking at the code. And comments are added by using a double / and then whatever text you want. Comments make it easier to navigate the code. I don't necessarily agree with that. It makes it easier in the sense that rather than setting and reading the structure of the text to determine what its function is, you could just read the comment and say, oh, I'm not concerned about that, and move on. Comments do not influence or affect code execution. Comments can be inserted anywhere in the code. And the start of a comment and the end of a comment has an asterisk, or with the /. Assignments are used to change the value of a or the memory location to which the tag points. Tag is the tag name, and then your operator is the : equal, and that's the assignment operator, and expression, where tag represents the memory location that is getting the new value. The tag must be in one of these atomic data types. The : equal is the assignment symbol, and the expression represents the new value to assign to the tag. So the expression could be a quite convoluted mathematical expression that references many tags, but the result of that expression, based on the equal sign, will be put into the tag that's at the head of the expression, the tag in green there. If your tag is Boolean, then it has to be a Boolean expression. If it's a single integer, double integer, real, then we use a numerical expression. And of course, the semicolon ends the assignment. I/O modules update memory asynchronously, meaning we're talking about primarily the passive backplane, the 1756 passive backplane, and even so true with some of the 1769. The controller does not go over the backplane and collect data from the I/O modules. The I/O modules will update memory locations asynchronously with the program execution. Not so with Studio5000 and MicroLogic. You can't execute code and simultaneously update I/O. If you need the input data to remain constant for each reference, you must buffer the input data. In other words, the very first code that you execute in the continuous task are simply move statements that move the data from an IO tag to an internal tag, and then you use the internal tags all the way throughout your code. And even though the IO tags change value, asynchronous from the program, they are only moved into the internal tag position at the beginning of the scan of the logic. Therefore, they won't change during the execution of the logic. It's good to buffer your IO to get dependable, or I should say the most repeatable, the most deterministic. Non-retentive assignments. A non-retentive assignment is reset to 0 each time the controller enters the run mode or leaves the step of a sequential function chart that is configured for auto reset, and you have embedded the assignment in an action step or use the action to call a structured text routine with the JRSR. Honestly, I threw this in here, but if you've not done structured text before, this really doesn't mean a whole lot. And if you've not done sequential function charts before, it really doesn't mean a whole lot. So maybe I should have left this statement out, but I'm going through the characteristics of structured text anyway. The syntax is tag. This is non-retentive. This is how you create a non-retentive assignment. You put the assignment operator inside of brackets. Tag represents the memory location. The assignment symbol is in brackets, and the expression represents the new value to assign to the tag. So the rules are exactly the same, other for non-retentive, you want brackets around your assignment symbol. Assigning ASCII characters to a string. This follows the same format as all of the others, except that you are assigning a character to an element of a string. So in this case, for the tag string 1, you are assigning a value of 56 to the very first character, character 0. You can also use the character of another string to declare the value for this string. String 02.data position 0 or element 0, character 0, it is a value, it's a character, and you're assigning it to string 01 data position 0. To add characters to a string, use the concatenation function. To insert characters into a string, use insert. An expression, again, is a tag name, equation, or comparison. It's an expression. To write an expression, use any of these elements. Tag name that stores the value, or it's a variable, or it points to the memory location. Number you enter directly into the expression, like a constant, also called an immediate value. Functions such as absolute, truncation, we showed you a whole list. Operators such as plus, minus, less than, greater than, equal, and, or, nor, etc. Those are operators. When writing expressions, follow these points. Use any combination of uppercase and lowercase letters. Example, for the and, uppercase A and D, just the A uppercase or no uppercase. Typically, I do all uppercase for these operators and functions. For complex situations, use parentheses to group expressions within expressions. This again allows easier reading and clarifies the execution. Expressions, operators, and data types. For these functions, use these operators and use these data types for optimal performance. So if you want to add, use the plus operator and always add double integers or real. Same thing with subtract or negate. You're probably thinking, why double integers and real? Why not single integers and integers? Well, the native data type for the 32-bit memory of the Logix engine is double integer. So in many cases, if you're going to work with single integers or integers, it may convert it to a double integer to do the operation and then convert it back to whatever data type that you selected for the result. It's always better to work with double integers and real than the other atomic data types for these operators. Multiply, use an asterisk. Exponent, x to the power of y, double asterisk. Divide, /. Modulo divide, MOD. Here are, again, expressions, operators, and data types. So you can see these are all numeric expression operators. We mentioned these before. And notice that some of them you would use a dent or a real, and others you can only use a real. You're probably thinking, why can I only use a real for some of these trigonometric functions? Well, that's because it's going to come back as a floating point. It's not always going to be a whole number. I think you knew that. Here's some logic that I threw in the lab. I had you do some ladder logic diagram, looks like 3 of them, a couple function block diagrams, and some structured text. In other words, I had you put code that was somewhat equivalent into these different routines. But because we're using the same tag names for all these different routines, in the main routine, you had to have this logic. Whichever one you selected, it turned off the others so you weren't getting interference. For instance, if I enabled ladder logic diagram 1, if you look down through there, you'll see that it's unlatching everything else. Enable LLD_01 through a one-shot, unlatches LLD02, LLD03, function block diagram 1, function block diagram 2, and structure text 1. If you look down through the code, you'll see that it follows suit. This is the front-end presentation for languages of the Logix engine, a PLC professor presentation on structured text. I'm sure that you gathered through watching this video, if you've watched many of my others, that I was not really passionate and demonstrative when I was doing this presentation. I felt obligated to do something on structured text. The problem is I do not use a lot of structured text. When I do, it's mostly for math functions, and it's in a separate routine because I always make algebraic expressions, which I've been doing for many years, including the compute instruction and ladder logic. Doing math in structured text is relatively simple for me. But anything beyond that, even though I full well understand if, then, else, while, repeat, until, etc., it is not my first choice for doing most types of logic, and I think you clearly sensed that in this presentation. I wish that I could have given you more. This is what I had to give you on structured text. The labs are good. You do the labs and you'll have a good start with structured text. Thank you for watching.